These are the examples for Algebra 2B, Credit 1, Lesson 13.1. Lesson 13.1, we're going to be talking about, well, starting off with transformations on exponential functions. Got a lot of information up here, but it's stuff that we've seen before. The transformation rules are and what the different letters A, H, and K, and that's what we're really paying attention to here, what they do to the graph. And it's the same as we saw with all other types of equations previously, what the A, H, and the K do. So we'll just briefly review that. Remember that if A is negative, that's going to reflect the graph vertically over the x-axis. If the absolute value of A, meaning just the numerical part of A, in other words, not important whether it's positive or negative, if that's between 0 and 1, that's going to be a vertical compression. If it's greater than 1, it's a vertical stretch. Now notice, just like in the other functions that we saw, the H has a minus in front of it, so it's counterintuitive, and hopefully we're getting used to that by now. If we have a plus H in the equation, that's going to move the graph or translate it to the left. Minus H goes to the right. K is the nice one. It does what you think it will. Plus K moves us up. Minus K will move us down. So let's take a look at our transformations for an example for problem number 1. So notice here, there's nothing. So this number here, the 8, that's B, the base of the exponential function. There's no number written here, so we're going to assume that it's a 1. Remember, if that's a positive 1, there is going to be no effect on the graph because we're only concerned with whether if A is negative or if it's between 0 and 1 or greater than 1. But if it's exactly 1, there's no effect on the graph. So we only have 2 transformations here, the effect of this minus 2 and the effect of this plus 5. Well, the minus 2 is in the position of H. Minus H is going to move us to the right. So that's going to translate as another way to say that it's moving or shifting. So translate 2 units to the right. And then the plus 5, that's in the position of K. Plus moves us up. So that's going to translate the graph 5 units up. And that's it. Those are the 2 transformations that are created by the numbers, the minus 2 and the plus 5. All right, let's take a look at an example for problem number 2. And as we work here in this little area, because we got a graph coming up for number 3. So let's take a look at an example for number 2. For number 2, we have the function g of x equals negative 3 times 7 to the power of x minus 1. So notice this time we do have a number in the place of a. Remember, this 7 is the base. So we're not going to concern ourselves with that. Only with a, if there is an h, and if there is a k. So first of all, we notice that a is negative 3. The negative, remember, if a is negative, that's going to reflect us over the x-axis. So we start with a reflection over the x-axis. And next, the 3 here. So we have a 3. So the absolute value of a, the absolute value of negative 3 is 3. And since that's more than 1, that's going to be a vertical stretch as opposed to a vertical compression by a factor of that number, by a factor of 3. And notice not negative 3. We're only concerned with the numerical part, not whether it's positive or negative. Now notice there's just x here. There's no number. Well, I guess you can say there's a 0. But if h is 0, if there's no number there, we're not concerned with any left or right transformation. So the only other thing to concern ourselves with is with this minus 1 that is not with the x. It's outside the exponent. So that's in the position of k. Minus moves us down. So that will translate the graph down 1 unit. So translate down 1 unit or 1 unit down, however you want to say that, Either way is acceptable. And that's it. Those are the three transformations: reflection over the x-axis, vertical stretch by a factor of 3, and translating the graph 1 unit down. And again, pause, rewind, study the rules here. But right now, if you want to pause, now would be a good time because we're going to shift over to the graph. No pun intended. So let's go ahead and get rid of this. We got a little bit less going on here. And let's go ahead and translate over to the right here to our graph. And so what we want to do, our example for number 3, it says we want to write the exponential function that is represented by this graph using the parent function f of x, which is given here. And hint, helpful information will be highlighted or boxed. That's in your packet. All right, so let's take a look here. So what we need to do is identify the b, which is the base, h, which is, as we already discussed there, is with x in the exponent. We need to identify k, and we have this little equation to solve for a. So the first thing, b is the base, and that's given, but we want to make sure that we understand that that number, the 5, represents the base. So we are going to identify that, even though it's given. H, now, so how do we identify h? So h is, notice here in our graph, there's 2 reference points, 2, 3, and 3, 19. Now, we're only dealing with the first reference point. The first reference point is the reference point that is closest to this dashed line here, the asymptote. And so this second reference point that's way up here won't even come into play. But it is there. It will be there in your packets. And so we do want to point that out. So h is the x-coordinate of the first asymptote. Excuse me, of the first reference point. So h would be 2. So again, h is the x-coordinate, the first number in the ordered pair from that first reference point. K comes from the asymptote, and k here would be the asymptote is going through -1 on the y-axis, so k is -1. And now for a, we have this little equation to solve for a. We have a plus k equals y. K we already know is -1. Y comes, you might have guessed it already. If you want, try and guess at it. I guess I kind of pointed at it. But it's the y coordinate. We said it, but if you wanted to pause the video, anyway, it's too late. The y coordinate from that first reference point. And then all we have to do is solve this little equation. We're focused on the left because that's where a is. We got that -1, so we're going to get rid of it by adding 1. The 1's cancel, and we know that a is 4. And so now all we're going to do is plug in our numbers for a, h, and k. So we have f of x equals 4. Now, of course, this is b, but we already were given that, so we'll just leave it there. And now that we have a number for a, we do need to put the parentheses around the 5. Otherwise, that's going to look like 45. And then we have x minus h. H is 2. So x minus a positive 2 plus k plus a -1. K is -1 or just -1. And so the equation for this graph would be 4 times 5 to the power of x minus 2 plus 1. And so that is our example for problem number 3. Problem number 4, we're going to be looking at another graph, very similar here. So let's go ahead and get rid of all of this. And we're going to use that again. So let's go ahead and get rid of that. Let's put up the number 4 here for problem number 4. And here we go, our example for this one here. So let's go ahead. We have a reference. We have our asymptote going through 5. So let's go ahead and draw that first. And this one, what we're going to see here is a exponential graph, but that's kind of a hint here as to what's coming. That is facing downward. That's going to be below the asymptote. So it's been reflected over it. Hopefully that's a little bit of a hint. So we've got -2 and 3. So let's go ahead and put that point here. And that is our reference point. And actually, we're not going to spend time with another reference point. We'll just sketch that in like this. And so if there is a second reference point given, so remember the first reference point is the one that's closest to the asymptote. For this one, let's see. Actually, we would have another reference point at -1 and -3, I believe. Let's go ahead and sketch that in here, just so we get practice with that. Let me just double check, make sure that's right. Yeah, that looks good. All right. So again, just because you're going to see it there, we'll put it there, but that just as quickly we're going to cross it out because that second reference point, the one that's furthest away from the asymptote, is not going to come into play. All right. So now for number 4, our given parent function is going to be a times 4 to the x minus h plus k. And so once again, we need to identify the b, h, k, and a. B, of course, is the base that's given, so that's 4. Remember, h is the x coordinate of that first reference point, so h is -2. K is where the asymptote passes through on the y-axis, so that's at 1, 2, 3, 4, 5. So K is 5. And then we solve this little equation here, again, to find the value of A. We know that K is positive 5. Y, remember, is the y-coordinate from that first reference point, which is 3. And then to solve for A, we subtract 5 to both sides. Kind of running out of room here. 3 minus 5 is -2. And so A is -2. Substituting those values in for A, H, and K, A is -2. And of course, the base is already there, 4. We have X minus H, that's minus a -2. We'll write it in like that, but then we'll do some simplifying. K is positive 5, so we have a positive 5 over there. Remember, a minus, subtracting a negative becomes addition. And so our final answer, f of x equals -2 times 4 to the x plus 2 plus 5. And that's our answer for our example for problem number 4. All right, very good. All right, so now the last two, we're going to be working with Desmos. So let's come back. We're going to need some space over here. And let's see here. So we'll just kind of, in case you want to pause and look at that, study the problem, we will give you a chance to do that. All right, that should be enough time to pause it. If you missed it, go ahead and rewind it, and you can pause it there. So now, for number 3 and 4, again, we're going to be using Desmos. We're going to develop the equations, and then we'll use Desmos to solve. All right, so it says, write the functions and graph on Desmos. Use the graph to answer the question. We're going to round our answers to the nearest tenth, which is 1 decimal place. All right, it says 40 rabbits are introduced into a small uninhabited island. They have no predators, and food is plentiful on the island. So all that means is the scarcity of food or any predators has no effect on the population. Thus, the population will grow exponentially, increasing by 50% per year. In how many years will there be 200 rabbits on the island? All right, so in our example for number 5, we're going to have 30 rabbits. And they're going to grow by 40%. And we want to know when there's going to be 100 rabbits. All right, so we're going to have our exponential function. We're going to write that in the form of, now, remember our exponential is y times y equals, we can use f of x notation, but just for simplicity, we'll use y. We have y equals a times b to the x. In place of b, though, we have a growth rate here of 40%. So what we're going to do is, in place of b, we're going to use 1 plus r. All right, so now, what do we substitute in? So A is our starting population of 30. Our growth rate is 40%. As a decimal, that would be 0.4. Remember, to make a percent a decimal, You move the decimal point 2 places to the left. So we have 1 plus 0.40 to the power of x. So that's our first equation. Our second equation is just y equals what we were trying to see how long it takes the population to grow to. So that's just y equals 100. All right, so now we're going to take those equations, functions, or equations, I guess we should say, type those into Desmos. So let's go ahead and do that. And we'll share the screen here for Desmos. And we have, let's get rid of that. We don't need that. All right, so here we go. All right, so we're going to type those in. We have y equals 30 times 1 plus, now you could also simplify that. 1 plus 0.40 would just be 1.4, but we can just leave it like that. And then to get into the exponent, you can bring up the keyboard, click a to the power of b. That brings you into the exponent, and then type your x. And depending on where your graph is centered, you might see the equation already there. Our other equation is just y equals 100. We're just trying to see how long it takes the population to reach 100 rabbits. Now, what you're going to have to do is scroll out, maybe click and drag the graph down. And once you find where the, and what we're looking, I guess we should say is what we're looking for is where the two graphs, the exponential and that horizontal line, y equals a number is always going to be just a horizontal line. Where they intersect, we'll zoom in on that a little bit. But what we're going to do is click on one of the graphs, and the reason we're going to zoom in, we get a couple gray dots here. This one here on the y-axis, if we're close to the y-axis, they are going to give us the y-intercept, but that's not what we're trying to find here. We're trying to find where they intersect. And where they intersect is right here at 3.57. Let's try and keep that up there. 3.57 and 100. So they want us to round to the nearest tenth. So we have 3.57. We're going to round to the nearest tenth. 5 is in the tenths spot. So remember, when we round, we can either stay that number, 3.5, or go up to 3.6. The next number, it determines that. Remember, 0, 1, 2, 3, 4 are stay numbers. 5, 6, 7, 8, 9 are go up numbers. The next number is a 7. That's a go up number. So we're going to go up to 3.6. So it's going to take 3.6. Remember, our time was in years. So 3.6 years for that rabbit population to grow from 30 to 100 rabbits in 3.6 years. Hopefully we can see that on the board okay. And we can also see that there on the graph. All right, so now let's take a look at an example for problem number 6. Problem number 6, it says, and this is another example of exponential growth. Mindy has a watch that was from her great-grandfather. She had it appraised and finds that it's worth $3,500. She wants to sell it, but the appraiser tells her that the value is appreciating, growing by 7% per year. So maybe she wants to keep the watch. And how many years will the value of the watch be? $7,000. All right. So for number 6, a similar situation. It may not sound similar because in number 5, we're talking about population of rabbits. In number 6, we're talking about the value of something, in this case, a watch. But let's take a look here. We have, we're going to say we have a watch worth $2,000. It's going to grow by 5% a year. And we want to know when it's going to be worth double that value, $4,000. So how long to $4,000? All right, so now 5%, we're going to need that as a decimal. Now, when it's a single-digit percent, be careful, because 5% as a decimal is not 0.50. 0.50 is, this would be incorrect. It's not 50%. For the moment, let's unshare the screen so we can see that. And so it would not be 0.50 because 0.50 is 50%. Make sure we can see that okay. And let's see, make sure everything is in the screen. Yeah, I think so. So 0.5 or 5% as a decimal, we move it 2 to the left. That creates a blank there. So it's 0.05 would be 5% written as a decimal. So our first equation will be using that same format again. Y equals a times 1 plus r to the power of x. A is our starting amount again. So 2,000. R as the decimal is 0.05, and we have x is our exponent. Our other equation is just y equals the value that we want to see how long it takes the watch to grow to. So we'll go ahead and enter the equations. Let's go ahead and share our screen again. And there we go, Desmos. And there we go. All right, let's get rid of the equations that we had. So we got y equals 2,000 times 1.1 plus 0.05 to the power of x. Remember how we do that? We bring up our keyboard, click A to the B. That brings us into the exponent, and we type our x. Our other equation is just y equals 4,000 because we're trying to determine how long it will take for that watch to grow to 4,000. Now, we don't see anything here because the graphs aren't within our field of view. If you ever get confused where you are on the graph, you can just click this home key. That'll reset things. Now, that doesn't help too much because we don't see the graph. So we're going to zoom out. We have bigger numbers here. We're in the thousands this time. So now we see the exponential graph. We have to get all the way up to 4,000. So as you can see, we're only at 1,000. But as we scroll out, we quickly get there. And now we're going to put our cursor over that point. We're going to zoom in. And click on one of the graphs. Remember, not the y-intercept point, not where x is 0. We're going to go over here, and we see that the value will be 4,000 in 14.20 years. So again, we're going to round to the nearest 10th. So we're rounding to where the 2 is. The next number is a 0. So our options are to stay 14.2 or to go up to 14.3. Again, the next number is a 0. 0 is a stay number, so that would be 14.2. So in about 14.2 years, although can't know the future for sure, but we would expect the value of that watch to be about $4,000 in 14.2 years. All right, let's go ahead and unshare the screen. So that's it for this lesson. Remember, pause, rewind the videos to get the best understanding and study, as you pause it, study the examples. Again, rewatch it if you need to, and I'm sure you're going to do great with the work. So until the next video, and of course, ask questions too. Till the next video, take care and God bless. Good luck with the work. Bye-bye.